Right now, as you listen to these words, light from a star 4 years away is just beginning its journey toward Earth. 4 years of traveling at 299,792 kilometers every single second, and it still has not arrived. At that speed, light circles our entire planet 7 times before you finish reading this sentence. Yet the nearest galaxy, Andromeda, sits so impossibly far away that its light takes 2.5 million years to reach your eyes. You are looking at ancient history painted across the sky. The visible universe stretches 93 billion light-years from edge to edge, and for over a century, physics has declared with absolute certainty that nothing, no rocket, no signal, no whisper of information, can ever cross those distances faster than light permits. The speed limit is not a law written by governments. It is stitched into the geometry of existence itself, woven into every atom, every force, every tick of every clock that has ever measured time. But in 1994, a physicist named Miguel Alcubierre discovered something extraordinary hiding inside Einstein's own equations. A geometry that does not break the speed limit but makes it irrelevant. Space itself, it turns out, has no speed limit. And that single distinction opens a door so dangerous that the universe appears to guard it with layers of impossibility stacked like fortress walls. Prepare for a journey through warped space-time and forbidden mathematics. We begin. Close your eyes for a moment and imagine something simple. Imagine you are standing in an open field at night, and above you, the sky is filled with stars. Each one of those tiny points of light is a sun, burning with nuclear fire, hanging at distances so vast that the numbers used to describe them lose all human meaning. The nearest star beyond our own sun sits roughly 4 light-years away. That means light itself, the fastest thing the universe permits, takes 4 full years of relentless travel just to cross that gap. And light does not dawdle. It moves at approximately 299,792 kilometers every single second. In 1 second, a beam of light could circle the Earth more than 7 times. In the time it takes you to blink, light has already traveled a distance your car would need hours to cover. Yet even at that breathtaking pace, light needs 4 years to reach the nearest neighboring star. The galaxy stretches 100,000 light-years across. The observable universe spans 93 billion light-years from edge to edge. These distances are not simply large. They are a kind of prison, built not from walls or bars, but from the geometry of reality itself. Now here is where most people misunderstand the speed of light. They think of it as a speed limit, the way a highway has a speed limit, a number posted on a sign that you could theoretically exceed if you built a fast enough engine and were willing to accept the consequences. But the speed of light is nothing like that. It is not a rule imposed from outside, like a law passed by some cosmic government. It is a property, is of the fabric of existence. The speed of light is built into the relationship between space and time themselves. It is the rate at which causality moves through the universe, the rate at which one event can influence another, the conversion factor between distance and duration. It appears not just in equations about light, but in equations about gravity, about nuclear forces, about the structure of atoms, about the behavior of electric and magnetic fields. Tampering with it would not just change how fast things can travel. It would change everything. Chemistry would unravel. Atoms would behave differently. The stars would burn at different rates, or not at all. Biology, as we know it, depends on molecular bonds that depend on forces, that depend on constants, that depend, ultimately, on the speed of light, d. This is what makes the cosmic speed limit so different from every other barrier humanity has ever faced. When people said we could never flee, the barrier was engineering. When they said we could never split the atom, the barrier was technology. When they said we could never reach the moon, the barrier was resources and will. But when physics says nothing can travel faster than light, the barrier is not technology or engineering or resources. The barrier is the structure of space-time itself. You cannot build an engine powerful enough to break it, because the concept of breaking it contains contradictions that go deeper than any engine can reach. Think of it this way. You are walking along a road that stretches toward a mountain in the distance. With every step you take toward the mountain moves 2 steps farther away. You can walk forever and never arrive, not because you are slow, not because the mountain is far, but because the geometry of the path itself prevents arrival. The speed of light works in a similar way. As you accelerate toward it, the very nature of space and time shifts around you, conspiring to keep that final threshold forever out of reach. Time slows down, mass increases, energy requirements climb toward infinity. The universe reshapes itself to enforce its own rules, not through force, but through structure. And yet, something remarkable hides inside the mathematics of the very theory that established this barrier. Albert Einstein, the man who showed us why nothing can travel faster than light, also gave us a framework in which space itself has no such restriction. The same equations that forbid you from outrunning a photon also permit the fabric of space to stretch, compress, and ripple, at any rate whatsoever. Distant galaxies already recede from us faster than light, carried along by the expansion of space between us. They do not violate any law because they are not moving through space faster than light. Space itself is expanding, carrying them along, the way a river carries a leaf. The leaf does not swim, the river moves. This distinction, so subtle it took physicists decades to fully appreciate, opened a door that would lead to some of the most extraordinary theoretical proposals in the history of science. If space can move faster than light, and if objects can ride that movement without themselves exceeding the speed limit through their local surroundings, then perhaps the cosmic speed limit is not quite the absolute prison it first appeared. Perhaps it is more like a wall with a hidden passage. A passage that does not break the wall, but passes through it in a way the wall's own architecture permits. What physicists discovered in the decades following Einstein's work was not a way to violate the speed of light. It was something stranger, and in many ways more profound. A way to make the speed limit apply to everything inside a bubble of space, while the bubble itself glides through the cosmos, unbound by that same limit. The passengers obey every law, the vehicle obeys none. And the universe, for reasons we are still struggling to understand, seems to allow this distinction while fighting with every weapon in its arsenal to prevent anyone from ever exploiting it. The story of how we arrived at this understanding begins not with warp drives, or exotic matter, or warped geometry. It begins with a young man sitting in a patent office in Switzerland, staring at a contradiction in the equations of light, and deciding that the entire world's understanding of space and time must be wrong. That young man was 26 years old, in 1905. His name was Albert Einstein, and in that single year, he published 4 papers that would quietly demolish 2 centuries of physics built on Isaac Newton's foundations. He did not set out to discover a cosmic speed limit. He set out to resolve a puzzle that had been bothering physicists for years. James Clerk Maxwell's equations for electromagnetism predicted that light always travels at the same speed, regardless of how the observer moves. This flatly contradicted Newton's simple and intuitive rule that velocities add together. Throw a ball from a moving train, and the ball moves faster relative to the ground than relative to you. That made perfect sense for trains and balls, but Maxwell's equations said light does not work that way. Light moves at the same speed, no matter what. Einstein chose to trust Maxwell, and in doing so, he shattered our understanding of time, space, and motion forever. Einstein's decision to trust Maxwell's equations led him somewhere no physicist had dared to go before. If light truly travels at the same speed for every observer, regardless of how fast they move, then something else must change to make that possible. Something fundamental, something everyone had always assumed was fixed and reliable. That something turned out to be time itself. Picture this carefully. You are standing on a train platform. Your friend is aboard a train, moving past you at tremendous speed. You both watch a beam of light travel from the floor to the ceiling of the train car. Your friend, sitting inside the train, sees the light go straight up, a simple vertical path. But you, standing on the platform, see something different. Because the train is moving sideways relative to you, the light appears to travel a longer diagonal path. It goes up and sideways at the same time. Now here is the key. Both of you must measure the same speed for that light beam. Maxwell's equations demand it. Experiments confirm it. The speed of light is identical for both of you. But if the light travels a longer path from your perspective, while moving at the same speed, then it must take more time to complete that journey from your perspective. Time passes differently for you than for your friend on the train, not because your clocks are broken, not because of some trick of perception. Time itself flows at different rates, depending on how you move relative to each other. This was Einstein's shattering insight. Time is not universal. It is not a single river flowing at the same pace for everyone, everywhere. Time is personal. It depends on your motion. Two people moving relative to each other experience different amounts of time passing between the same two events. This is called time dilation, and it is not a theory waiting for confirmation. It has been measured with extraordinary precision using atomic clocks flown on aircraft, placed aboard satellites, and tested in particle accelerators, where tiny particles moving near light speed survive far longer than identical particles sitting still in a laboratory. The global positioning system in your phone depends on this effect being real, and satellites orbiting Earth move fast enough and sit high enough in Earth's weaker gravity that their clocks tick at slightly different rates than clocks on the ground. Without corrections based on Einstein's equations, GPS would drift by kilometers within a single day. Every time your phone tells you where you are, it is quietly confirming that time bends with motion and gravity. Exactly as Einstein predicted, more than a century ago. But time dilation was only the beginning of the strangeness. Einstein showed that space itself also changes depending on your motion. Objects moving at high speed appear compressed in their direction of travel. This is called length contraction. A spaceship flying past you at 90% of light speed would appear squeezed, shorter along its direction of motion than it would appear sitting still. The passengers aboard would notice nothing unusual. To them, their ship looks perfectly normal. But from your perspective, the ship has physically shrunk. Space itself has contracted along the axis of motion. And then came the revelation that would haunt every future dream of faster-than-light travel. Einstein showed that space and time are not separate things. They are woven together into a single, four-dimensional fabric called spacetime. You cannot change one without changing the other. Motion through space affects your experience of time. Your position in a gravitational field affects how fast your clock ticks. Space and time are partners in a dance so intimate that separating them is like trying to separate the North Pole of a magnet from the South. They come as a package, always together, always intertwined. This unification of space and time carried a consequence so profound that its full implications are still being explored today. Einstein demonstrated that mass and energy are also related, connected by the most famous equation in all of science. Energy equals mass times the speed of light squared. That tiny letter C, representing the speed of light, appears here not as a speed limit for travel, but as a conversion factor between mass and energy. It tells you how much energy is locked inside matter. And because the speed of light is such an enormous number, squaring it produces a truly staggering conversion rate. A small amount of mass, it contains an almost unimaginable amount of energy. This is why nuclear weapons are so powerful. They convert tiny amounts of matter into enormous amounts of energy, following Einstein's equation precisely. But this equation also works in reverse, in a way that devastates any hope of reaching light speed. As you accelerate an object, you pump energy into it. That energy, according to Einstein's equation, adds to the object's effective mass. A heavier object requires more energy to accelerate further, which adds more mass, which requires still more energy. The process feeds on itself in a vicious spiral that climbs toward infinity as the object approaches light speed. You are not just fighting friction or air resistance, like you are fighting the structure of space-time itself, which converts your acceleration energy into additional mass, making further acceleration progressively harder. There is something almost poetic about this trap. The faster you go, the heavier you become. The heavier you become, the harder it is to go faster. The universe does not slam a door in your face. It simply makes the hallway stretch longer with every step you take. Gentle and absolute and utterly inescapable. No amount of fuel solves the problem. No engine design overcomes it. The barrier is not in the engineering. The barrier is in the mathematics of how energy, mass, space, and time relate to each other at the deepest level physics has ever reached. Einstein did not set out to imprison humanity within a cosmic speed limit. He set out to understand why light behaves so strangely. But what he found was that the strangeness of light reveals the true nature of the universe. A universe where time bends, space contracts, mass grows with velocity, and the speed of light stands not as a wall to be broken, but as a pillar holding the entire structure together. Remove it, and everything collapses. Every atom, every force, every clock, every star. And yet, as we are about to discover, this same pillar casts a shadow, and in that shadow, numbers begin to whisper something extraordinary about what happens when you push closer and closer to that forbidden threshold. Let us now step inside those numbers and feel what happens as a spacecraft pushes closer and closer to the speed of light. Not in abstract theory, but in concrete, measurable consequences. That pile on top of each other like weight stacking onto a bridge. That was never built to hold infinity. Imagine a spacecraft accelerating away from Earth. At low speeds, everything behaves exactly as Newton predicted centuries ago. Push harder, go faster. Double the thrust, double the acceleration. The universe feels cooperative and obedient, like a machine responding predictably to your inputs. But as the spacecraft climbs past 10% of light speed, past 20%, past 50%, the rules begin to shift beneath your feet, like sand moving under a wave. The cooperation fades. The machine, it starts resisting. At 90% of light speed, roughly 270,000 kilometers per second, the changes become impossible to ignore. Time aboard the spacecraft now passes at roughly half the rate experienced by observers watching from Earth. For every 2 hours that tick by on Earth, only 1 hour passes aboard the ship. The spacecraft itself appears compressed in its direction of travel, squeezed shorter than its resting length, and its effective mass, the resistance it offers to further acceleration, has grown substantially beyond what it weighed sitting still on a launch pad. The energy bill for each additional kilometer per second of velocity has already climbed far beyond what simple physics would predict. Push harder. Reach 99% of light speed. Now, time aboard crawls at roughly 1/7 the Earth rate. 7 hours pass on Earth for every single hour the crew experiences. Mass has increased by a factor of 7. The spacecraft that weighed 1,000 tons at rest now behaves as if it weighs 7,000 tons when you try to push it faster. And here is where the mathematics turns cruel. Getting from 99% to 99.9% of light speed requires more energy than the entire journey from 0 to 99%. Everything you spent reaching 99%, all that fuel, all that thrust, all that effort, you would need more than all of it again, just to cross that tiny remaining fraction. At 99.9% of light speed, time dilation reaches a factor of 22. The crew ages 1 year, while Earth ages 22 years. Mass has ballooned to 22 times its resting value. The energy required for further acceleration has become something difficult to express in human terms. Stars burn for millions of years producing energy. The energy needed to push a single spacecraft through these final fractions of light speed would exceed what some stars produce in their entire lifetimes. Climb to 99.999%, 5 nines after the decimal point. Now the dilation factor exceeds 700. A single day aboard the ship corresponds to nearly 2 years on Earth. The effective mass has multiplied 700-fold. A spacecraft that originally weighed 1,000 tons now resists acceleration as though it weighs 700,000 tons. The energy required to push it even slightly faster would exhaust the total output of entire suns. Not the energy a sun produces in a year, the energy a sun produces across its entire billions of years of burning. And still, the speed of light remains unreached. Still, that final threshold sits ahead, shimmering, untouchable, separated from you by a gap that grows narrower in velocity, but wider in energy with every increment you gain. This is what physicists call an asymptotic barrier, a limit you can approach forever without ever reaching, like a curve on a graph that bends closer and closer to a line, but never quite touches it, no matter how far you extend it. The curve and the line live in the same mathematical space, but they never meet, yet your velocity can climb to 99.99999% of light speed, adding nines after the decimal point until you run out of breath counting them. Each 9 costs more energy than all the previous 9s combined, and after all those 9s, after exhausting the energy output of galaxies, you are still not there. You are still traveling slower than light. this is not a wall you can break through with a bigger hammer. There is no wall. There is a curve that bends away from you as you approach, always receding, always just out of reach, requiring infinite energy to close a gap that never fully closes. The universe does not say no with a barrier. It says no with geometry. The shape of the relationship between energy and velocity simply does not permit a massive object to reach light speed. The mathematics is not complicated. It is a simple equation, elegant and absolute, and it yields infinity at precisely the point where velocity equals the speed of light. Infinity is not a large number. It is not a number at all. It is a statement that the question has no answer. How much energy does it take to accelerate a massive object to exactly light speed? The question has no answer. The mathematics returns infinity, which means the operation cannot be performed. Not with difficulty, not with enormous resources. It simply cannot be done within the framework of physics as we understand it. There is a strange and haunting speculation that lives at the edges of this mathematics. Some physicists have wondered about hypothetical particles called tachyons, particles that would always travel faster than light, never slower. In the equations of special relativity, tachyons would possess imaginary mass, a quantity involving the square root of negative numbers. They would lose energy as they speed up and gain energy as they slow down. Slowing to light speed would require infinite energy for a tachyon, just as reaching light speed requires infinite energy for ordinary matter. The speed of light becomes a barrier from both sides. Ordinary matter can never reach it from below. Tachyons, if they exist, could never slow to it from above. The two realms of velocity would be forever separated, with light speed standing as an uncrossable boundary between them. No experimental evidence for tachyons has ever been found. They remain a mathematical curiosity, a ghost in the equations that probably signifies nothing physical. But the asymptotic prison carries implications beyond mere energy costs. Something deeper and more disturbing lurks in the mathematics of objects approaching light speed, something involving the very ordering of events in time, the sequence of cause and effect. That makes the universe make sense. And as we are about to discover, this ordering is far more fragile than anyone imagined. Before Einstein revealed how deeply motion entangles with the flow of time, there is something the universe protects even more fiercely than its speed limit, something so fundamental that without it, physics itself would dissolve into meaningless noise. That something is causality, the simple, sacred ordering of cause before effect. You strike a match, and then the flame appears, never the other way around. You throw a stone into a pond, and then the ripples spread outward. The ripples never gather themselves together and launch a stone into your hand. This ordering of events, cause first and effect second, is not just a pattern we observe. It is the backbone of every physical law ever written. Without it, prediction becomes impossible. Science becomes impossible. Reality as we understand it becomes impossible. And faster than light travel, if it were ever achieved by any object moving through space, would shatter this ordering beyond repair. Understanding why requires grasping something Einstein revealed about the nature of simultaneity. In everyday life, two events either happen at the same time, or they do not. This seems like an obvious objective fact about the universe. If two firecrackers explode at the same instant, they explode at the same instant for everyone, everywhere. What could possibly be controversial about that? Einstein showed that this intuition is wrong. Simultaneity is not absolute. It depends on how you are moving. Two events that appear simultaneous to one observer can appear to happen at different times to another observer moving relative to the first, yet neither observer is mistaken. Neither clock is broken. The universe genuinely presents different time orderings to observers in different states of motion. Let us make this concrete. Imagine two lightning bolts strike opposite ends of a long train platform at exactly the same moment, as measured by someone standing precisely in the middle of the platform. This observer sees both flashes reach her eyes at the same instant, and concludes the strikes were simultaneous. Fair enough. Now consider a passenger on a train racing through the station at high speed. This passenger is also sitting in the middle of the train, but the train is moving toward one lightning strike and away from the other. Light from the strike ahead reaches the passenger first, because the passenger is rushing toward it. Light from the strike behind arrives later, because the passenger is moving away from it. After careful analysis, accounting for light travel times, the passenger concludes that the two strikes were not simultaneous at all. One happened before the other. Here is the critical point. Both observers are correct. There is no deeper truth that makes one right and the other wrong. Simultaneity itself is relative. It depends on your motion. This is not a philosophical opinion. It is a mathematical consequence of the constancy of light speed, confirmed by every experiment ever designed to test it. Now, this relativity of simultaneity becomes truly dangerous when applied to events separated by vast distances. For events that are far enough apart that light cannot travel between them in the time separating them, different observers can disagree not just about whether the events are simultaneous, but about which event happened first. Observer A might see event 1 happen before event 2. Observer B, moving at a different velocity, might see event 2 happen before event 1. Both are correct within their own reference frames. The time ordering of such events is genuinely observer-dependent. In our normal, slow-moving world, this disagreement about ordering never causes problems, because no information can travel between such events fast enough to create a contradiction. The speed of light acts as a guardian, ensuring that disagreements about time ordering never lead to paradoxes. Its causes always precede their effects for all observers, because the influence connecting cause to effect travels at or below light speed. But introduce a faster than light signal, and this protection vanishes instantly. Imagine you send a message to a friend on a distant planet using some hypothetical faster than light transmitter. From your perspective, the message travels forward in time, departing today and arriving at the distant planet a few moments later. Perfectly sensible. Your friend receives the message and immediately sends a reply using the same faster than light method. From certain reference frames, observers moving at particular velocities relative to you and your friend, this reply travels backward in time. The mathematics here is not ambiguous, it is precise and unavoidable. If faster than light signals exist, some observers necessarily see those signals arriving before they were sent. Now combine these two transmissions. Your original message goes forward in time to your friend. The reply comes backward in time to you. The reply arrives at Earth before you sent your original message. You are now holding a response to something you have not yet said. You could read the reply, decide not to send the original message, and create a contradiction that has no resolution. If you never sent the message, how did your friend know to reply? If the reply prevented the message, what caused the reply? These are not clever word puzzles. They are genuine logical contradictions that emerge directly from the mathematics of special relativity whenever faster than light information transfer is permitted. The equations do not merely suggest these paradoxes, they demand them. Any mechanism that transmits information faster than light, whether it involves physical travel, energy beams, or quantum effects, creates reference frames in which effects precede their causes. The consequences of broken causality extend far beyond amusing paradoxes. If causes can follow effects, the entire structure of physical law collapses. Every equation in physics assumes that the state of a system at one moment determines its state at the next moment, not the previous one. Remove the ordering of time, and you remove the foundation on which every prediction, every measurement, and every scientific understanding rests. The past becomes as uncertain as the future. History becomes fluid, changeable, contradictory. The universe ceases to have a single coherent story and dissolves into a chaos of competing timelines that contradict each other. This is why physicists regard the speed of light not merely as a speed limit, but as a causality preservation mechanism. It ensures that the universe maintains a consistent ordering of events for all observers. It guarantees that causes always precede their effects, regardless of how fast you move or where you stand. The speed limit is not protecting a number, it is protecting the logical structure that makes reality coherent. There is an open and fascinating debate among theoretical physicists about whether certain exotic configurations of space-time might permit limited forms of faster-than-light travel without creating causal paradoxes. Some researchers have proposed that specific geometries might restrict superluminal travel to one-way paths that cannot be combined into the round trips necessary to create contradictions. Others invoke the idea that quantum gravitational effects we do not yet understand might automatically destroy any configuration approaching a causality violation. The universe, they suggest, might protect itself from paradox through mechanisms we have not yet discovered. These remain open questions without definitive answers. But what we know with certainty is that any form of faster-than-light travel must somehow address the causality problem, or accept the destruction of cause and effect as a consequence. And it is precisely here, at this seemingly impassable boundary, that Einstein's deeper theory begins to whisper about something remarkable. A way in which space itself might move without anything inside it ever exceeding that sacred speed, without any signal ever traveling backward through time. A possibility hidden not in the physics of motion, but in the physics of gravity, curvature, and the bending of space-time itself. 11 years after Einstein rewrote the rules of space and time, he did something even more extraordinary. He reimagined gravity itself. In 1916, he completed a theoretical framework called general relativity, a framework that would transform our understanding of the cosmos so completely that we are still absorbing its implications more than a century later. And buried within this framework lies the subtle distinction that would eventually make physicists dare to dream of reaching the stars. Before Einstein, gravity was a mystery wearing a mask of simplicity. Isaac Newton had described it beautifully. Every object with mass attracts every other object with mass. The force depends on how massive the objects are and how far apart they sit. This description worked brilliantly for centuries. It predicted planetary orbits, explained tides, guided cannonballs through the air. But Newton himself admitted he had no idea how gravity actually worked. How does the sun reach across 93 million miles of empty space and pull on the Earth? What carries that influence? How does it arrive? Newton had no answer. He described what gravity does, without ever explaining what gravity is. Einstein provided the explanation, and it was nothing anyone expected. Gravity is not a force at all. Gravity is geometry. The presence of mass and energy warps the fabric of spacetime itself, curving it the way a heavy bowling ball curves a stretched rubber sheet. Other objects moving through that curved spacetime follow the straightest possible paths available to them, paths called geodesics. But because the spacetime itself is curved, those straightest paths appear curved from an outside perspective. We perceive this curvature as gravitational attraction. Think about what this means. In the simplest terms, when you drop a ball, it does not fall because Earth reaches out with an invisible hand and pulls it downward. It falls because Earth's enormous mass has bent the spacetime around our planet, and the ball simply follows the curved geometry. The ball is not being forced anywhere. It is coasting along the most natural path available, through warped terrain. There is no force, only shape. No pull, only curvature. Gravity is the shape of spacetime telling matter how to move. This geometric picture of gravity has been confirmed with breathtaking precision. During solar eclipses, astronomers have measured starlight bending around the sun by exactly the angle Einstein's equations predict. Light follows curved spacetime just as matter does, tracing paths warped by the sun's mass. Atomic clocks placed at different altitudes tick at slightly different rates, because time itself flows differently depending on how deep you sit in a gravitational field. Clocks on mountaintops tick faster than clocks in valleys. Clocks aboard GPS satellites tick faster than clocks on Earth's surface. Without corrections based on general relativity, your phone's navigation would drift by kilometers within hours. Most dramatically, gravitational waves have been directly detected. These are literal ripples in the fabric of spacetime, produced when massive objects like black holes or neutron stars collide and merge. The LIGO detectors, instruments sensitive enough to measure changes smaller than the width of a single proton, have captured these waves exactly as Einstein's equations predicted. Spacetime is not a metaphor. It is a real, dynamic, physical medium that stretches, compresses, vibrates, and carries waves across billions of light years. Now, here is where general relativity opens a door. That special relativity seemed to seal shut forever. Special relativity established that nothing can move through space faster than light. General relativity kept that rule completely intact. Objects traveling through spacetime remain bound by the cosmic speed limit, without exception. But general relativity added something new and crucial. It revealed that spacetime itself is not bound by that same limit. Space can expand, contract, ripple, and warp at any rate whatsoever. This is not speculation. We observe it happening on the grandest scales of the cosmos. During cosmic inflation, in the first unimaginably tiny fraction of a second after the Big Bang, space expanded so rapidly that regions originally right next to each other ended up separated by distances far greater than light could have traveled in that time. This expansion did not violate relativity, because nothing moved through space faster than light. Space itself stretched, carrying everything along with it. Today, this expansion continues. Galaxies at the far edges of the observable universe are receding from us at velocities exceeding the speed of light. Light that left those galaxies billions of years ago is only now reaching our telescopes, because the space between us has been expanding throughout that entire journey. Those distant galaxies are not racing through space at superluminal speed. The space between us and them is growing. The cumulative effect of this growth over billions of light years produces recession velocities well above 300,000 kilometers per second. Consider an ant walking across the surface of a balloon that someone is inflating. The ant moves at ant speed across the rubber surface. It obeys its own little speed limit perfectly, but two dots drawn on the balloon can separate from each other faster than the ant could ever walk, because the balloon surface itself is expanding. The ant follows its rules. The balloon follows different rules. Both coexist without contradiction. This is the crucial distinction that changes everything. Moving through space and being carried by space are fundamentally different things, governed by fundamentally different constraints. Objects moving through space-time cannot exceed light speed, but space-time itself, the medium through which they move, has no such restriction. It can stretch, shrink, and carry things along. At any rate, the geometry permits. And this distinction, once fully understood, planted a seed in the minds of physicists that would take decades to germinate. If space can expand faster than light, carrying galaxies along at superluminal velocities without violating any law, might it be possible to engineer a local region of space-time that moves through the broader universe at faster than light rates? Could you create a small pocket of flat, calm space, embedded within a wave of contracting and expanding geometry that surfs through the cosmos at arbitrary speed? The passengers inside would sit motionless relative to their local surroundings. They would obey every law special relativity demands. But their little pocket of calm space would ride a wave of space-time geometry that carries them across the universe. Faster than light could manage traveling through normal, unwarped space. It sounds impossible, or it sounds like a trick, a play on words rather than a genuine physical possibility. But Einstein's own field equations, the mathematical heart of general relativity, contain solutions describing exactly this kind of configuration. And in 1994, a physicist named Miguel Alcubierre would write those solutions down for the first time, giving mathematical form to humanity's oldest dream. In 1994, a Mexican physicist named Miguel Alcubierre sat down with Einstein's field equations and asked a question that no one had formally posed before. Instead of starting with a known arrangement of matter and calculating what space-time geometry it would produce, he worked backward. He started with the geometry he wanted and solved for what kind of matter would be needed to create it. The geometry he wanted was simple in concept and staggering in implication. A bubble of perfectly flat, calm space-time that moves through the broader universe at any speed whatsoever, including speeds far exceeding light. What Alcubierre discovered was that Einstein's equations accepted this geometry without complaint. The mathematics did not reject it. The field equations treated this warp bubble solution with the same validity they give to the equations describing black holes, gravitational waves, and the expanding universe. It was an exact solution, rigorous and self-consistent, sitting right there inside the theory of general relativity, like a hidden room in a house you thought you knew completely. The Alcubierre metric, as it came to be called, describes something both elegant and almost dreamlike in its simplicity. Picture a region of flat space-time, ordinary space where physics works exactly as it does in your living room. No curvature, no strange forces, no warping of time. Now surround that flat region with a shell of intense space-time curvature. Ahead of the flat region, as space contracts violently, squeezing distances into smaller and smaller volumes. Behind the flat region, space expands dramatically, stretching distances apart. The contraction ahead and expansion behind create a wave of geometry that propagates forward through the broader universe, carrying the flat interior along with it. Think of a surfer riding an ocean wave. The surfer does not move through the water. The wave moves through the water, and the surfer rides the wave. The surfer's speed relative to the water beneath the board is essentially zero, but the wave carries the surfer forward, at whatever speed the wave travels. The warp bubble works similarly, but in the fabric of space-time itself. The spacecraft sits motionless relative to the flat space inside the bubble. It obeys every law special relativity imposes. But the bubble, the wave of contracting and expanding geometry, propagates through the universe at superluminal velocity. The spacecraft never exceeds the speed of light through its local space. Space itself does the moving. Or consider a simpler picture. Imagine standing on a moving walkway at an airport. Your feet are still relative to the surface beneath them. You are not walking. You are not running. You are standing perfectly still on a surface that happens to be gliding forward through the terminal. Now imagine that walkway could move at any speed, even faster than you could ever run. You remain stationary on its surface, obeying your personal speed limit completely. But the walkway carries you faster than that limit would otherwise allow. The warp bubble is this walkway, built not from rubber and metal, but from the curved geometry of space-time. The contraction of space ahead of the bubble is crucial to understanding why this works. When space contracts in front of the ship, distances in that direction shrink. A journey of 100 light years might involve crossing only a tiny amount of actual space, if that space has been sufficiently compressed. The destination that seemed impossibly far away becomes effectively closer, because the intervening space has been squeezed into a smaller volume. Meanwhile, the expansion behind stretches the space already traversed, lengthening the distance between the ship's starting point and its current position, as measured through normal space. From outside the bubble, observers would witness something extraordinary. A spacecraft entering the warp field would appear to stretch and blur, its light becoming increasingly redshifted as the bubble accelerated. Then, it would vanish entirely, as the bubble achieved superluminal velocity. No light from inside could escape to reach external observers. Once the bubble moved faster than light relative to its surroundings, the bubble would cross interstellar distances in what appeared to external observers as impossibly short times. A journey to Alpha Centauri, 4 light-years away, might take days or even hours, depending on how fast the bubble propagated. When the bubble stopped and the spacecraft emerged, it would have effectively traveled faster than any light signal could have completed the same journey through normal, unwarped space. Yet nothing inside the bubble ever exceeded light speed relative to its local surroundings. The passengers would have felt no acceleration, experienced no crushing forces, detected no time dilation beyond what they started with. They would simply have been carried along by the geometry of space-time, passengers on a wave that space creates, and space carries forward. This is what separates the Alcubierre proposal from naive faster-than-light concepts. The speed limit applies to motion through space-time. It does not apply to the motion of space-time itself. Just as cosmic expansion carries distant galaxies away from us at superluminal recession velocities, without anything moving through space faster than light, a warp bubble would carry its contents across the cosmos, while obeying all local speed constraints. The limit is not broken, it is relocated. The spacecraft respects the law, while space-time itself finds a way around it. Alcubierre's paper sent a quiet shockwave through theoretical physics. Here was a geometry permitted by Einstein's own equations that achieved effective superluminal travel without violating any fundamental principle of relativity. The mathematics was clean, the logic was sound, the solution was exact. For the first time in the history of physics, faster-than-light travel had a rigorous mathematical framework, grounded in our best theory of gravity and space-time. But then Alcubierre performed the calculation that would cast a long shadow over every warp drive proposal that followed. He, having written down the geometry he wanted, he plugged it back into Einstein's equations and asked the obvious question: what kind of matter would you need to actually produce this geometry? What would you have to place around the flat region to create the contracting space ahead and expanding space behind? The answer arrived, like a cold wind. The warp bubble requires negative energy density, not low energy, not zero energy. Energy less than nothing. Energy below the vacuum of empty space. A form of matter that would need to possess gravitational properties opposite to everything ever observed in nature. Matter that pushes space-time apart instead of pulling it together. Matter that repels instead of attracts. Matter that might not exist in any usable form, anywhere in the physical universe. The door that Einstein's equations had opened now revealed a corridor stretching into darkness, lined with barriers that would make the original speed limit seem almost gentle by comparison. The mathematics had granted permission. Now physics would begin extracting its price. Negative energy. The phrase itself sounds like something borrowed from science fiction, a concept too strange to belong in serious physics. Yet, it emerges directly from the most rigorously tested theory of gravity ever constructed. The warp bubble geometry that Einstein's equations so readily accept demands matter with properties unlike anything humans have ever held, measured, or observed at meaningful scales. And this demand reveals the first layer of what would become an ever-deepening fortress of constraints, surrounding the dream of faster-than-light travel. To understand why negative energy is necessary, consider what the warp bubble geometry requires. The contraction of space ahead of the bubble needs something that pushes space-time together from the front. The expansion behind needs something that pulls space-time apart from the rear. Normal matter cannot accomplish either task in the required direction. Normal matter creates attractive gravity. It pulls things together. It curves space-time inward, creating the familiar gravitational wells that hold planets in orbit and keep your feet on the ground. What the warp bubble demands is the opposite. It needs matter that curves space-time outward, creating gravitational repulsion rather than attraction. Only matter with negative energy density could produce the specific curvature pattern the Alcubierre metric requires. Now here is where the story takes a surprising turn. Negative energy is not entirely unknown to physics. Quantum mechanics, the theory governing the behavior of particles at the smallest scales, predicts that certain very specific configurations can produce tiny regions, where energy density drops below the energy of empty vacuum. The most famous example is the Casimir effect, first predicted in 1948 and experimentally confirmed in 1997 with remarkable precision. The Casimir effect works like this. Take two uncharged metal plates and place them extremely close together in a vacuum, separated by a gap smaller than a human hair. Quantum mechanics tells us that even empty space is not truly empty. It seethes with virtual particles, brief fluctuations of energy that pop in and out of existence constantly. Between the two plates, these fluctuations are restricted, only certain wavelengths of virtual particles can fit in the narrow gap. Outside the plates, no such restriction exists. The result is that fewer virtual particles exist between the plates than outside them. This imbalance creates a measurable force pushing the plates together. More importantly for our story, the region between the plates contains slightly less energy than the surrounding vacuum. Its energy density is negative relative to empty space. This effect is real. It has been measured in laboratories with extraordinary accuracy. Negative energy density exists in our universe. The laws of physics permit it. But the gap between the Casimir effect and a functional warp drive is so enormous that it borders on the absurd. The Casimir effect produces negative energy densities measured in millionths of a joule per cubic meter. Alcubierre's original calculations suggested that the warp bubble would require negative energy equivalent to the total mass energy of an entire star. Converting a star's mass into energy through Einstein's famous equation produces a number so large that writing it out would fill a page with zeros. The Casimir effect provides a whisper of negative energy. The warp drive demands a thunderstorm. Subsequent work by other physicists managed to reduce this impossible requirement somewhat. In the late 1990s, physicist Chris van den Broek showed that clever manipulation of the bubble geometry could shrink the exterior size of the bubble while maintaining a large flat interior through extreme spacetime curvature. This trick reduced the energy budget from universal scales down to something equivalent to a few solar masses. Still absurd by any practical standard, but a dramatic mathematical improvement. Later, physicist Harold White at NASA proposed that oscillating the bubble walls in specific patterns might reduce energy requirements even further, potentially down to hundreds of kilograms of negative energy, rather than stellar masses. These claims generated excitement and media attention. Hundreds of kilograms still exceeds anything achievable through known quantum effects by enormous factors. But the number at least became something a human mind could visualize without collapsing under the weight of zeros. However, at every one of these reductions has been challenged by other researchers who identified overlooked factors or mathematical errors in the optimistic calculations. The true minimum energy requirement for a functional warp bubble remains uncertain and deeply controversial. What is not controversial is that even the most optimistic estimates demand quantities of negative energy that exceed what any known physics can supply by many orders of magnitude. And nature appears to have built additional safeguards to ensure that negative energy never accumulates in useful quantities. In the 1990s, physicists Lawrence Ford and Thomas Roman discovered mathematical relationships called quantum inequalities that place strict limits on how much negative energy can exist, where it can exist, and how long it can persist. These inequalities function like cosmic lending rules. You can borrow negative energy from the quantum vacuum, but the loan comes due almost immediately, and with steep interest. The more negative energy you create in a region, the more positive energy must appear nearby to compensate. The larger the region of negative energy, the faster the compensation must arrive. The longer you try to maintain negative energy, the more aggressively nature demands repayment. These are not engineering constraints that better technology might overcome. They appear to be fundamental features of quantum mechanics, woven into the mathematical structure of the theory as deeply as the speed of light is woven into relativity. Nature enforces a strict energy accounting that seems specifically designed to prevent macroscopic regions of sustained negative energy from existing. There is a speculative idea that lives at the edges of this problem, one that some physicists find intriguing even though it has no experimental support. Dark energy, the mysterious force accelerating the expansion of the universe, behaves in some ways like negative energy on cosmological scales. It produces gravitational repulsion, pushing galaxies apart rather than pulling them together. Could dark energy be harnessed or concentrated to fuel a warp bubble? The honest answer is, we have no idea. We do not understand what dark energy is. We cannot manipulate it. We cannot concentrate it. We barely know it exists, except through its gravitational effects on the largest observable scales. Suggesting it could power a warp drive is like suggesting that ocean currents could power a time machine. The connection between the known phenomenon and the desired application exists only in imagination. The exotic matter problem therefore stands as the first great barrier beyond the mathematical permission Einstein's equations provide. The geometry works on paper. The equations balance. The solution is exact and valid. But producing that geometry requires ingredients. The universe seems determined not to provide in useful quantities. The mathematics opens a door, physics locks it, and swallows the key. Yet, as researchers would soon discover, the exotic matter problem was not the warp drive's greatest challenge. It was merely the outermost wall of a fortress, with walls within walls, each one revealed only when you managed to see past the one before it. And behind the exotic matter barrier lay problems so severe they would make the energy challenge seem almost gentle by comparison. Imagine you have somehow solved the exotic matter problem. Imagine some future breakthrough in quantum physics. Hands you all the negative energy you need, packaged neatly and ready for use. You construct your warp bubble, climb inside your spacecraft, and prepare to ride a wave of space-time geometry across the stars. You would expect your problems to be over. They are only beginning. Because behind the wall of exotic matter stands a series of deeper barriers, each one independently capable of making faster-than-light travel impossible. And each one emerges not from engineering limitations, but from the fundamental physics of how warp bubbles interact with space-time itself. The first of these deeper problems involves something physicists call a horizon. The moment a warp bubble accelerates to superluminal speed, the flat region inside becomes causally disconnected from the warped region ahead. This means that no signal, no light beam, no information of any kind can travel from the interior of the bubble to the leading edge where space is contracting. Light from the spacecraft races toward the front of the bubble at 300,000 kilometers per second, but the bubble wall ahead recedes faster than light. The signal can never catch up. It is like trying to shout a warning to someone running away from you faster than sound can travel. Your voice never reaches them, no matter how loudly you scream. This creates a devastating problem for navigation. Once the bubble achieves superluminal velocity, the occupants have absolutely no way to steer it. They cannot send course corrections to the bubble wall because their signals cannot reach it. They cannot slow down, speed up, or change direction. They are passengers inside a geometry they can no longer influence, hurtling through the cosmos on whatever trajectory was set before the bubble went superluminal. If an obstacle appears ahead, they cannot avoid it. If their destination has moved, they cannot adjust. If anything goes wrong, they cannot respond. The stopping problem proves equally devastating. How does a superluminal warp bubble come to rest? The occupants cannot command it to stop because their signals cannot reach the bubble boundary. Some external mechanism would need to operate from outside the bubble at the destination. But who positions themselves at a distant star system to stop an incoming warp bubble? how would they know precisely when it was arriving? How would they coordinate with occupants they cannot communicate with? Each question opens onto deeper impossibilities. The same physics that permits superluminal travel forbids any reasonable method of controlling that travel. You cannot have one without sacrificing the other. These are not problems waiting for clever engineering solutions. They emerge from the fundamental geometry of the warp bubble itself. The causal disconnection between interior and exterior is not a design flaw that could be fixed with better technology. It is a mathematical consequence of superluminal propagation. See, any bubble moving faster than light necessarily creates a horizon that isolates its interior from any ability to influence its trajectory. The permission and the prison come as a single package. Some theorists have suggested pre-programming the bubble with a fixed trajectory before departure. The geometry would contain encoded instructions that unfold automatically, guiding the bubble to its destination like a ballistic missile following a pre-calculated arc. But interstellar space is not empty. It contains roughly 1 atom per cubic centimeter on average, plus cosmic rays, photons, magnetic fields, and gravitational anomalies from unseen masses. A pre-programmed trajectory calculated from billions of kilometers away cannot account for conditions discovered along the way. Navigation without the ability to adjust course is not navigation. It is a blind leap across a minefield. Beyond the horizon and control problems, the warp bubble encounters another formidable adversary. In 1992, physicist Stephen Hawking proposed something called the chronology protection conjecture. This idea suggests that the laws of physics conspire to prevent the construction of any configuration that would allow time travel or causal paradoxes, even when specific solutions to Einstein's equations seem to permit them. Hawking's conjecture has never been proven as a rigorous mathematical theorem, but 3 decades of theoretical investigation have provided it with substantial support. The connection to warp drives is direct. A superluminal warp bubble enables travel between distant points faster than light could manage through normal space. As we explored earlier, this creates the potential for causal paradoxes, scenarios where effects precede causes and contradictions destroy the logical structure of physics. Hawking's conjecture suggests that nature would actively prevent such configurations from forming through whatever mechanisms are necessary to preserve causality. The most studied such mechanism involves quantum effects at the bubble boundary. Calculations show that the extreme spacetime curvature at the edge of a warp bubble would generate intense radiation, similar to the Hawking radiation, produced by black holes at their event horizons. See, the violent transition between normal space and the warped geometry of the bubble wall would tear virtual particles from the quantum vacuum in enormous quantities. This radiation would concentrate precisely at the boundary layer where the bubble geometry is most delicate, attacking the structure exactly where disruption matters most. This particle creation drains energy from whatever source maintains the warp configuration. For a superluminal bubble, where energy requirements already strain the boundaries of imagination, this additional drain could become so severe that it destroys the bubble before it achieves its intended purpose. The radiation would not merely weaken the configuration, it would destabilize it catastrophically, collapsing the carefully constructed geometry into chaos and releasing enormous energy in the process. This pattern reveals something profound about the relationship between classical and quantum physics. Classical general relativity, the theory of spacetime geometry, permits warp bubble configurations without objection. The field equations accept them as valid solutions. But quantum mechanics then imposes additional constraints that make those configurations unstable or unrealizable. The classical theory opens a door. The quantum theory slams it shut. Every time physicists have combined quantum mechanics with another branch of physics, the combination has proven more restrictive than either theory alone. Quantum gravity, the complete unification of general relativity and quantum mechanics that we do not yet possess, would almost certainly impose even more severe constraints on exotic spacetime configurations. There is an open and fascinating debate among physicists about whether these quantum instabilities truly kill all warp configurations or only certain ones. Some researchers believe that specific bubble geometries might avoid the worst quantum effects through careful design. Others argue that the instabilities are fundamental and unavoidable, rooted in principles that no geometry can circumvent. The question remains unresolved because answering it fully requires a complete theory of quantum gravity, which remains one of the greatest unsolved problems in all of physics. What emerges from this analysis is a picture of layered defenses. The universe does not guard its speed limit with a single wall. It guards it with walls behind walls, moats behind moats, traps behind traps. Solve the exotic matter problem and you face the horizon problem. Address the horizon and you encounter quantum instabilities. Work around instabilities and causality constraints appear. The barriers operate not as independent obstacles, but as an interlocking network, where solving one problem simply relocates the impossibility to another part of the structure. And as physicists would soon discover, even the most creative recent proposals to eliminate these barriers would reveal this pattern. Repeating at ever deeper levels of physical law, the exotic matter problem haunted warp drive research for decades. It seemed like the single point of failure. The one lock that needed picking before faster-than-light travel could move from mathematics to reality. Many physicists reasoned that if negative energy could somehow be eliminated from the requirements, the path to the stars would finally open. This assumption drove years of theoretical work exploring whether warp-like geometries could be constructed using only positive energy, the ordinary matter and energy that fills our universe. What these efforts uncovered was not a breakthrough, but a deeper understanding of why the universe resists faster than light, travel through multiple independent mechanisms rather than just one. One promising class of proposals involved what physicists call subluminal warp drives. These are configurations that produce warp-like effects, contracting space ahead and expanding it behind, but at speeds below the speed of light. Some of these solutions can indeed be constructed using only positive energy, avoiding the exotic matter requirement entirely. The mathematics works cleanly, the geometry is consistent, the energy conditions are satisfied. At first glance, this seems like genuine progress. If you can build a slow warp drive with ordinary matter, perhaps you can gradually scale it up to superluminal speeds through careful refinement. But the transition from subluminal to superluminal is not a smooth ramp you can climb gradually. It is a cliff. The two regimes differ in fundamental ways that become apparent only through detailed mathematical analysis. A subluminal warp bubble maintains causal connection between its interior and exterior. Light signals can pass back and forth between inside and outside. Control remains possible. Navigation remains conceivable. The physics stays manageable. A superluminal bubble severs this connection completely and permanently. The interior becomes causally isolated from everything external. The horizon structures that form at superluminal speeds change the physics in ways that cannot be smoothed over or gradually approached. Whatever energy advantages subluminal solutions offer simply do not extend to the superluminal regime. Building a slow warp drive teaches you nothing useful about building a fast one, because the two problems are fundamentally different. Not different in degree, like the difference between a hard problem and a harder problem. Different in kind, like the difference between swimming and flying. Another approach that generated considerable excitement involved constant velocity warp drives. These are configurations where the warp bubble maintains a fixed speed rather than accelerating or decelerating. Some of these solutions can be constructed with positive energy alone, avoiding exotic matter entirely. The mathematics is elegant, the geometry is valid, the energy conditions are met, headlines announced breakthroughs, excitement built among researchers and the public alike. Then the catch revealed itself. Constant velocity warp bubbles cannot be created from flat spacetime using positive energy. They cannot be stopped or dissipated back into flat spacetime using positive energy. They must have always existed and must continue existing forever. They are eternal features of spacetime geometry that either exist from the beginning of the universe or do not exist at all. They cannot be manufactured, launched, navigated, or decommissioned. They are permanent cosmic structures, not vehicles. Even if such bubbles exist naturally somewhere in the universe, perhaps formed during the violent conditions of cosmic inflation in the first fraction of a second after the Big Bang, they would be useless as transportation. You could not build one to carry you to Alpha Centauri. You could only hope to stumble upon one already moving in the right direction at the right speed. And since constant velocity bubbles cannot decelerate, riding one would mean an eternal journey with no stops. You board and you never get off. The bubble carries you past your destination at fixed speed, onward through the cosmos forever. This is permission taken to its most absurd and useless extreme. Soliton solutions represented yet another creative approach. These are self-reinforcing warp geometries that maintain their shape while propagating like waves that never lose energy or dissipate. A soliton is a wave that holds itself together through its own internal dynamics, requiring no external support once established. The concept is beautiful. The mathematics possesses genuine elegance. Soliton warp solutions are stable against small disturbances. They propagate smoothly. They look, on paper, like exactly what a warp drive should be. But Soliton solutions encounter the same practical barriers as constant velocity configurations. Creating a soliton from flat spacetime, accelerating it to useful velocities, directing it toward a specific destination, and stopping it upon arrival all require operations that positive energy alone cannot perform. The soliton exists as a mathematical object of remarkable beauty that physical reality cannot build from scratch. It is a perfect vehicle that cannot be assembled, a flawless engine that cannot be started, a magnificent ship that cannot be launched. The pattern running through all these positive energy proposals is unmistakable and deeply revealing. Each one solves the exotic matter problem while simultaneously introducing new problems that prove equally or more severe. Remove the need for negative energy and you face the impossibility of creation or destruction. Achieve creation with positive energy at subluminal speeds, and you cannot cross the threshold to superluminal travel. Find eternal superluminal solutions, and you discover they cannot be controlled, stopped, or used for any practical purpose. It is as though the exotic matter requirement was not the enemy, but a load-bearing wall. Remove it without installing alternative supports, and the entire structure reveals deeper instabilities that the exotic matter constraint was somehow holding in check. The wall you thought was blocking your path was actually holding up the ceiling. Just knock it down, and worse things happen than the wall ever caused. This pattern suggests something profound about the architecture of physical law. The constraints preventing faster than light travel are not independent obstacles that might be defeated one at a time, like locks on a chain. They form an interlocking web where each constraint supports and reinforces the others. Solve one and the others tighten. Remove one wall and another rises to replace it. The universe does not guard its speed limit with a single mechanism that might be cleverly bypassed. It guards that limit with a self-repairing network of constraints that adapts to every theoretical assault. There is a speculative and somewhat unsettling idea that some physicists have entertained in response to this pattern. Perhaps the impossibility of faster-than-light travel is not just a consequence of known physical laws, but a fundamental principle from which those laws derive. Perhaps causality preservation and the speed limit are not rules that emerge from deeper physics, but axioms upon which all deeper physics is built. If true, no modification of our theories and no advancement in our understanding would ever open a path to superluminal travel, because the prohibition exists at a level more fundamental than any specific equation. Whether this philosophical position proves correct remains to be seen, but the practical reality it describes matches everything theoretical physics has discovered across decades of increasingly sophisticated investigation. And as we are about to explore, the full web of constraints extends even further than the proposals we have examined so far, reaching into the fundamental theorems of general relativity itself. Step back now and look at the full picture. Not just one barrier or two, but the entire web of constraints that the universe has constructed around its speed limit. What emerges is not a simple wall, but something more like an immune system, a layered, redundant, self-reinforcing defense that responds to every theoretical challenge by activating new mechanisms of resistance. Each constraint connects to others through deep principles that become visible only when you try to circumvent them. Pull one thread, and the entire fabric tightens around you. The focusing theorem represents one of the most fundamental strands in this web. General relativity requires that positive energy focuses geodesics, causing them to converge toward each other. This is a mathematical way of saying that ordinary matter creates attractive gravity. Things fall toward massive objects. Light bends toward stars. Particles curve toward planets. This focusing of paths through spacetime by positive energy is not a minor technical detail. It is one of the most fundamental features of how gravity works in Einstein's theory. Now consider what a warp bubble demands. The contraction of space ahead of the bubble requires geodesics to diverge, to spread apart rather than converge. This defocusing is the opposite of what positive energy produces. You need spacetime to push paths apart in front of the ship, but positive energy always pulls paths together. This is another way of arriving at the exotic matter requirement, approached from a completely different mathematical direction. The focusing theorem tells you that positive energy cannot produce the geometry a warp bubble needs ahead of it. No clever arrangement of ordinary matter changes this. No sophisticated engineering overcomes it. You cannot make positive energy defocus geodesics any more than you can make water flow uphill by reshaping the container. The behavior is intrinsic to the energy itself. Some researchers have explored whether quantum vacuum effects might achieve the necessary defocusing without violating the classical focusing conditions. The Casimir effect, as we explored earlier, demonstrates that quantum mechanics can produce small regions of negative energy density, but perhaps sophisticated arrangements of quantum vacuum states could cumulatively produce the required geometry through quantum rather than classical mechanisms. The quantum inequalities discovered by Lawrence Ford and Thomas Roman close this possibility with mathematical precision. These inequalities demonstrate that any negative energy produced by quantum effects must be compensated by positive energy nearby, with the compensation requirements growing more severe for larger regions and longer durations. The accounting is strict, and the interest rates are punishing. You can borrow negative energy from the vacuum, but the universe demands immediate repayment with extra positive energy added on top. The quantities of negative energy achievable through known quantum effects fall short of warp drive requirements by factors so enormous, they defy meaningful comparison. The gap is not a few orders of magnitude that improved technology might bridge. It spans 20 or 30 orders of magnitude, comparable to the difference between the mass of a single atom and the mass of an entire planet. No plausible extension of current physics closes such a chasm. Stability adds another devastating layer to the web of constraints. Even if you could somehow assemble the required geometry, maintaining it presents challenges that may be fundamentally insurmountable. Warp bubble configurations exist in extraordinarily delicate balance, so the extreme curvature at bubble boundaries amplifies any imperfections exponentially. Imagine a pencil balanced perfectly on its sharpened tip. Mathematically, this is a valid equilibrium. The forces balance. The pencil can theoretically remain upright forever, but the tiniest vibration, the gentlest breath of air, the smallest quantum fluctuation topples it instantly. The equilibrium is real, but unstable. Physical reality cannot maintain it. Warp bubbles resemble this balanced pencil, but in multiple dimensions simultaneously. Quantum fluctuations alone would destabilize most proposed configurations within timescales so short. They make the blink of an eye seem like an eternity. Maintaining a warp bubble long enough to cross interstellar distances would require control precision exceeding the quantum uncertainty limits that physics imposes on all measurements. You would need to control the geometry more precisely than the universe allows anything to be controlled. The laws of quantum mechanics themselves forbid the precision needed to maintain the configuration those same laws theoretically permit. The irony is almost elegant in its cruelty. Then there is the collision problem, a concern that grows more troubling the more carefully you examine it. Interstellar space is not perfectly empty. It contains roughly 1 atom per cubic centimeter on average, plus cosmic rays, photons, neutrinos, and streams of charged particles from stellar winds. A warp bubble traveling across light years of space would encounter enormous quantities of this material. What happens when interstellar matter contacts the bubble boundary remains a subject of active theoretical investigation, but none of the proposed outcomes are reassuring. Some calculations suggest that matter would accumulate at the leading edge of the bubble, compressed by the contracting space ahead into increasingly dense concentrations. By the end of a journey spanning several light years, the bubble would arrive at its destination surrounded by a shell of interstellar matter compressed to extreme densities and heated to staggering temperatures. The energy contained in this compressed shell could exceed nuclear weapons by factors limited only by journey distance. But arriving at your destination would mean arriving with a weapon of planet-destroying power, aimed at whatever you were hoping to visit. Your greeting would be annihilation. Other analyses suggest the matter might be deflected around the bubble rather than accumulated, redirected by the extreme space-time curvature, like water flowing around a stone in a stream. But even this more optimistic scenario involves extreme energy releases. Matter accelerated around the bubble boundary at near-light speeds would produce intense gamma radiation, particle showers, and other lethal emissions. A warp bubble crossing interstellar space might leave a trail of destruction behind it, irradiating everything along its path with killing intensity. Either outcome transforms the warp drive from a vehicle or into a weapon of unprecedented destructive power, regardless of its intended purpose. The space-time distortions involved could devastate planetary surfaces. The energy releases upon arrival could exceed anything in human history. Even a failed or unstable warp experiment could produce catastrophic effects extending across astronomical distances. Perhaps the universe's determination to prevent faster-than-light travel reflects something resembling cosmic safety. Perhaps the speed limit protects civilizations from technologies that would inevitably destroy them. Perhaps the prison is also a shelter, the walls that confine us also shielding us from powers we are not equipped to wield responsibly. What emerges from this complete survey of constraints is a picture of remarkable depth and interconnection. Exotic matter links to focusing theorems. Focusing theorems connect to energy conditions. Energy conditions relate to stability requirements. Stability requirements involve quantum fluctuations. Quantum fluctuations tie to causality preservation. Causality preservation connects to chronology protection. Each thread leads to others in a web of mutual reinforcement that grows stronger with every attempt to break through any single strand. And this web, as we will now discover, reveals something profound not just about warp drives, but about the fundamental relationship between mathematics and physical reality itself. There is a question that has haunted philosophers and physicists alike for thousands of years. What is the relationship between mathematics and reality? When an equation describes something beautiful and self-consistent, does that mean the thing it describes must exist somewhere in the physical universe? Or can mathematics imagine things that reality simply refuses to build? The story of the warp drive provides one of the most illuminating answers to this ancient question that modern physics has ever produced. Einstein's field equations accept the Alcubierre metric with the same mathematical hospitality they extend to the Schwarzschild metric describing ordinary black holes. Both are exact solutions. Both satisfy every requirement the equations impose. Both emerge from the same mathematical framework with equal legitimacy. Yet one describes objects astronomers observe throughout the cosmos. Black holes whose gravitational waves we have detected, whose shadows we have photographed, whose effects we have measured with extraordinary precision. The other describes something that may be fundamentally impossible to construct despite being mathematically identical in status. This asymmetry tells us something crucial. General relativity, despite its extraordinary success at predicting observable phenomena, does not provide a complete description of what can physically exist. The field equations provide necessary conditions for physical possibility, but not sufficient ones. A configuration must satisfy Einstein's equations to be physically real, but satisfying those equations does not guarantee physical reality. Additional filters operate that the classical equations alone do not capture. The mathematics is too permissive. Reality is more selective. The ancient Greek philosopher Plato believed that mathematical forms represented a deeper reality than physical objects. A circle drawn on paper is imperfect, but the mathematical concept of a circle possesses perfect precision. Plato thought the mathematical concept was more real than any physical drawing. Modern physics often seem to support this view. Einstein derived special relativity from mathematical reasoning before experiments confirmed time dilation. Paul Dirac predicted the existence of antimatter from the symmetries of his equations years before positrons were discovered in laboratory experiments. The mathematics seemed to know about reality before physicists did, as though equations were windows into truth rather than mere human inventions. Yet the warp drive phenomenon suggests a more complicated relationship. mathematics describes a vastly larger space of possibilities than physics ever realizes. General relativity's equations accept countless solutions describing configurations that the physical universe appears to contain none of. Closed time-like curves that would allow travel into your own past. Traversable wormholes connecting distant regions of space through shortcuts. Naked singularities where space-time curvature becomes infinite without being hidden behind an event horizon. Infinite energy densities concentrated at mathematical points, all mathematically valid, and all apparently physically forbidden. The equations do not distinguish between solutions that describe real things and solutions that describe impossible things. They treat the warp drive metric and the black hole metric with identical mathematical respect. The universe makes a distinction the equations cannot. Something beyond the field equations decides which solutions get built and which remain forever on paper. Some of these additional constraints come from quantum mechanics. The quantum inequalities that limit negative energy, the Hawking radiation that destabilizes exotic geometries, the uncertainty principles that forbid the precision needed to maintain delicate configurations, all of these emerge from quantum physics rather than from general relativity itself. When you combine classical gravity with quantum mechanics, the combination proves far more restrictive than either theory alone. This pattern has repeated throughout the history of physics. Every time two fundamental theories have been merged, the resulting unified framework has forbidden things that either theory separately would have permitted. Quantum electrodynamics, the merger of quantum mechanics with electromagnetic theory, imposed constraints neither theory contained individually. The standard model of particle physics, combining quantum mechanics with nuclear forces, restricts possibilities in ways neither predecessor anticipated. Quantum gravity, the still incomplete merger of general relativity with quantum mechanics, should prove no exception, and every indication suggests it will be even more restrictive than what we currently understand. There is a deep and open debate among physicists about what this pattern means for our understanding of physical law. One school of thought holds that mathematical elegance is a reliable guide to physical truth. Beautiful equations tend to describe real phenomena. Symmetry in mathematics corresponds to symmetry in nature. This view has impressive historical support, but the warp drive challenges it directly. The Alcubierre metric is mathematically elegant. Its geometry is beautiful. Its logic is clean and self-consistent. Yet beauty alone does not make it real. Another school of thought suggests that physics operates according to a principle of maximum restriction. The universe permits the minimum set of phenomena consistent with its fundamental structure, forbidding everything it possibly can while still remaining self-consistent. Under this view, the constraints preventing faster-than-light travel are not obstacles to be overcome, but expressions of the universe's deepest organizational principles. The speed limit is not a fence around a garden. It is the ground the garden grows in. Perhaps the most profound lesson the warp drive teaches us is about the nature of physical law itself. Laws of physics are not rules imposed on the universe from outside like regulations posted on a wall. They are descriptions of the universe's internal structure, expressions of how space-time, energy, matter, and information relate to each other at the most fundamental level. Yet you cannot violate them because they are not commands. They are descriptions of what reality is. Asking whether you can break the speed of light is like asking whether you can make a triangle with 4 sides. The question contains its own answer. A 4-sided triangle is not a triangle that is hard to build. It is a contradiction in terms. The warp drive research program, spanning 3 decades of sophisticated theoretical investigation, has not brought us closer to faster-than-light travel. But it has accomplished something arguably more valuable. It has illuminated connections between causality, energy, geometry, and quantum mechanics that might never have become visible through any other line of investigation. Each failed attempt to circumvent the speed limit has revealed new relationships between apparently separate physical principles. The web of constraints has become a map of deep structure, showing how different aspects of physics support and reinforce each other in ways that maintain the coherent, stable, predictable universe we inhabit. We learn about what is possible by carefully mapping what is not. The impossibility of warp drives is itself a discovery of profound importance. It reveals that the cosmic speed limit is not enforced by a single mechanism, but by an interlocking architecture of physical law so robust that no single breakthrough could ever dismantle it. The universe does not guard its structure with one lock that a clever key might open. It guards its structure with a self-reinforcing network of principles where each one holds the others in place. Remove one, and the rest shift to fill the gap. This is not a wall. It is the foundation of everything. And yet, standing here at the boundary between what mathematics permits and physics forbids, looking outward at stars we may never quickly reach, we find not emptiness, but something unexpectedly luminous. A kind of understanding that transforms cosmic imprisonment into cosmic belonging. The stars wait in silence. They have always waited. Long before human eyes first turned upward and wondered what those tiny points of light might be, the stars burned steadily in a darkness so vast that the numbers needed to describe it lose all human meaning. Our ancestors gathered around campfires and invented stories about those lights. They imagined gods and chariots and celestial rivers. They did not know that each faint glimmer was a sun, many larger than our own, hanging at distances that would take lifetimes upon lifetimes to cross even at the fastest speed the universe allows. We know now what they could not. We know the nearest star beyond our sun sits 4 light years away. We know our galaxy stretches 100,000 light years across and contains hundreds of billions of suns. We know the observable universe holds trillions of galaxies scattered across 93 billion light years of expanding space. And we know, with a certainty, that 3 decades of theoretical investigation has only deepened, that no shortcut through this immensity appears compatible with the fundamental structure of physical law. The warp drive journey began with mathematical permission. Einstein's equations accepted geometries that would carry spacecraft across the cosmos on waves of compressed and expanded spacetime. The Alcubierre metric demonstrated that general relativity does not forbid effective superluminal travel in the absolute way special relativity seemed to suggest. For a brief, exhilarating moment, the stars seemed within reach. The mathematics had opened a door that physics had appeared to seal forever. But each step through that door revealed another door beyond it, locked with different keys. Exotic matter requirements emerged first, demanding energy with properties that nature seems determined not to provide. Quantum inequalities imposed strict Lenin rules on negative energy, preventing it from accumulating in useful quantities. Horizon problems severed communication between bubble interior and exterior, making navigation and control impossible at superluminal speeds. Hawking radiation threatened to destroy bubble geometry through quantum particle creation at the boundaries. Chronology protection mechanisms appeared ready to destabilize any configuration approaching a causality violation. Focusing theorems forbade the spacetime geometry warp bubbles required from being produced by ordinary positive energy. Stability analysis revealed that proposed configurations would collapse under quantum fluctuations faster than they could serve any useful purpose. Collision calculations showed that arriving at a destination might mean arriving with planet-destroying energy concentrated at the bubble wall. Each barrier stood independently, each connected to the others through deep principles. Together, they formed not a wall, but an architecture of impossibility so thorough that solving any single problem simply exposed the others in sharper relief. The universe guards its speed limit, not with a single mechanism, but with a self-reinforcing web of constraints that grows stronger with every attempt to break through any single strand. Yet this journey through impossibility has not been wasted. Far from it. The decades spent exploring warp geometries have illuminated the structure of spacetime, the relationship between energy and curvature, the constraints governing physical configurations, and the profound connections between classical gravity and quantum mechanics. We have learned about what exists by carefully mapping what cannot. The impossibility itself has been a teacher of extraordinary generosity, revealing principles that might never have become visible through any other line of investigation. And the conclusion this teacher offers is not despair, but a strange and quiet form of peace. The constraints that prevent faster-than-light travel are the same constraints that make our existence possible. A universe where space-time geometry could be easily manipulated by engineering. Effort would be a universe where matter could not reliably organize into atoms, molecules, planets, or living beings. The stability of every chemical bond in your body depends on the constancy of physical law across space and time. If space-time could be casually warped, that constancy would dissolve. Chemistry would become unreliable. Biology would become impossible. The rigid structure that frustrates our travel ambitions is the same structure that enables our existence. The prison and the home are the same architecture viewed from different windows. This does not mean humanity will never reach the stars. It means we will not reach them through shortcuts. Interstellar travel through normal space, though requiring centuries or millennia, does not violate physical law. Generation ships carrying self-sustaining communities across the void. Seed ships carrying genetic information for reconstruction at distant destinations. Digital transmission of human consciousness at light speed followed by reconstruction. These approaches work within physics rather than against it. They require patience measured in generations rather than clever geometry measured in equations. But they are possible in ways that warp drives appear not to be. There is nobility in this acceptance. Human civilization has faced fundamental limits before and found wisdom rather than despair in acknowledging them. We cannot visit the interior of stars, but this impossibility taught us nuclear physics. We cannot observe particles without affecting them, but this impossibility taught us quantum mechanics. We cannot achieve perpetual motion, but this impossibility taught us thermodynamics. Each constraint initially seemed like failure. Each eventually revealed deep truths about the universe's structure that we could not have learned any other way. The speed of light joins this distinguished list of productive impossibilities, barriers that teach more than their absence ever would. Our species emerged on one small planet, orbiting one unremarkable star among hundreds of billions, in one galaxy among trillions. We have existed for a mere eye blink of cosmic time, appearing only in the last 100,000 years of a universe 14 billion years old. Yet, in that brief span, we have discovered the structure of atoms, the evolution of stars, the expansion of space, and the curvature of space-time. We have detected gravitational waves from colliding black holes billions of light years away. We have photographed the shadows of objects so massive that light itself cannot escape them. We have traced the afterglow of the Big Bang across the entire sky. A universe that produces beings capable of understanding it, even partially, is a universe containing something precious. That understanding matters regardless of whether it eventually carries us to distant stars or teaches us why such journeys must unfold slowly across deep time. The speed of light will stand. The mathematics that seemed to offer a way around it has instead revealed why the barrier exists and what it protects. We are not diminished by this knowledge, we are deepened by it. We understand our cosmic situation with clearer eyes than any generation before us. We know where we are, what surrounds us, and why the distances between stars are crossed, slowly or not at all. So let the stars wait in their silence. They have been patient for billions of years. They can be patient a little longer. And we, who learn to read the light they send across the void, who decoded the geometry of the space between us, who dared to ask whether that geometry might be bent in our favor and accepted the answer with grace, we too can be patient. Feel your breathing slow now. Feel the weight of your body settling into stillness. The equations are written. The constraints are mapped. The universe has shared its secrets, both the permissions and the refusals. Both are gifts. Both illuminate. Let the vast, quiet distances of space settle around you like a blanket woven from starlight and mathematics. You are here. You are made of the same atoms forged in those distant stars. You carry their light within you. And that is enough. That has always been enough.